We are FitCheck, and this is our final project for Stats 101A. So to give a little bit of context, League of Legends is a multiplayer online battle arena game that has been extremely popular. And so why does this matter to us? Well, our goal is to use data science to uncover patterns in the gameplay of League of Legends. And then you can use those insights to inform your gameplay strategy. So in a game of League of Legends, there is a blue team and a red team, and they both can acquire gold. Our guiding question today is, what explains the difference between the amount of gold acquired by the blue and the red teams? The data that we used was taken from 24,912 matches. The key variable that we're interested in is how much more gold the blue team obtained than the red team, and we'll call this the gold difference. In other words, a response variable is y equals gold diff. We'll look at multiple different features of each match to see if any of them can explain the gold difference. Some examples of these match features are the difference in experience level across the teams and the number of fire dragons that the blue team killed in this single game. Here we have a descriptive analysis of our data, and this is going to provide a preliminary look at the relationships between the difference in gold amounts and certain features. Most notably, there appears to be a strong association between gold difference and experience difference, and also between gold difference and champion level difference. Another thing to note is that some of the features did not have any meaningful data, so we decided not to include them in our model.
Our initial model was found by using the Bayes information criterion. By minimizing the BIC, we can find a model that only contains the significant predictors, so that we don't need to do separate t-tests for each predictor. In order to do the diagnostic for the initial model, we created a 4-plot graph. In the graph, we can find that the constant variance assumption is satisfied, while the normal distributed assumption was not satisfied at the two ends, and there is only one high leverage point. Since the leverage is within -4 to 4, it is not a bad leverage point. We use both the correlation graph and the VIF to assess the multi-collinearity. We identify the highly correlated predictors using the dark colors on the correlation map. In order to solve the problem of multi-collinearity, we remove predictors and only to keep the predictors with the most important features. For example, we choose to keep the difference of experience since it has a strong linear relationship with the response. After removing all unnecessary predictors, we get our final model. And it is fortunately that in our final model, all VIF are less than 5, which means they are not highly related. Now we need to do the model diagnostic again for the final model. We can see in the graph, the residuals of the final model has constant variance and normally distributed. There is only one high leverage point, and it is a good high leverage point, which means this is a good model to explain the relationship between variables in the game. The most important predictor in our model is the experience difference. It means that you can expect the red team has significantly less gold if they have less experience. Since our model has only a linear relationship, it will be easier to interpret compared to those with high power terms.